Thank you very much, Elizabeth, for the invitation and that I get to be the first talk. It's a pleasure. When I was preparing this talk, I was sort of conflicted because, there are many experts in the audience and in this program. And at the same time, if you haven't seen these things before, you can't just dive into the details. So in the end, I decided to make the talk, assuming nothing, or almost nothing of prerequisites. So with my apologies to the experts, if anybody wants to know more about the details of the proof, just send me an email. I'm happy to set up a Zoom meeting and talk more about the details. But for now, let's just start at the very beginning and talk about the history of this problem and some of the conceptual ideas that I want to discuss. So I should say up front, everything I'm going to talk about is joint work with Yair Shenfeld. Where does it start? Let's start with one of the classical results everybody knows, which is the isoperimetric theorem. Let me also say up front, I'm always going to be talking about convex bodies in this talk, so not general sets. So convex bodies are compact convex subsets in Rn, okay? And so we're talking about the isoperimetric theorem for convex bodies. What does it mean? Well, it says that among all bodies with a fixed volume, the surface area is minimized by the ball, right? Among bodies with fixed volume in Rn, so convex bodies in Rn, the surface area is minimized by the ball. By the Euclidean ball. And of course, everybody knows this. This is why soap bubbles are round, right? But if you say this theorem, one of the questions you might ask is, why do we just talk about surface area and volume, right? There are many other geometric parameters of convex bodies, So what if we also fix some other parameters? So not just volume and surface area, pick some other geometric parameter of convex bodies and let's fix it as well, and then ask the same question. It's a natural question. And historically, the very first question like this that was asked, at least to my knowledge, is about mean width. So let me remind you what the mean width is of a body. So if I have a convex body, I'll draw it in R2. So here is some convex body, K in R2. And now I pick a direction. Here I fix a direction X. Then what you can do is you can just sandwich the body between two planes that have that normal direction, right? So like this. And then this is the width of the body in that direction, right? So let's imagine you're measuring the width of a convex body using calipers, right? That's the width you get in that direction. But of course, you can change the direction of your calipers and you measure a different width in every direction. If you average over all directions, you get the mean width. Right, so the mean width is a perfectly reasonable and interesting geometric parameter of convex bodies, just like volume and surface area, right? So now you could ask the following question, right? Suppose that I take all convex bodies and I fix their volume, let's say to be 1, right? So now if I want to look at which one minimizes surface area, then that is the ball, right? But now suppose that in addition to fixing the volume to be 1, I also fix the mean width, but I fix the mean width to be, let's say, larger than the mean width of a ball with volume 1, right? And now I try to minimize surface area among that class of bodies, right? Well, if I fix the mean width to be larger than a ball, so I'm looking for a body that is wider than a ball, but still has volume 1 that minimizes the mean width, right? That can't be a ball because I'm asking for bodies that are wider than the ball, right? So what is the most efficient way, the minimal surface area way, right, to get a body of volume 1 that is wider than a ball? Oh, it has to stick out somehow, right? And now suddenly you're outside the usual theory of isoperimetric inequalities, right? I mean, you have here 2 parameters, right? It's an isoperimetric inequality involving not just volume, but also mean width. And you're trying to minimize surface area. So it's a very basic question. And usually when I'm giving the talk like this in person and I can sitting in a classroom and I can stare people in the eyes and ask them what they think, and then I can see everybody squirm, but it doesn't really work over Zoom, okay? But usually what people think is, oh, well, maybe it's an ellipse or something like that. That's the usual answer I get. But in fact, that's not the answer. The answer is very bizarre. The bodies that minimize look like this. So you start with a ball, right? So let me draw it in R3. So I have a ball here. But now what you do is you can take a point outside the ball and take its convex hull with the ball. And now you get an object that looks like this. It's a ball with like with a cone stuck on it. And I can do it again. For example, I can take another point outside the ball over here and stick it on, right? And now here's one example. So it's a ball that has 2 points outside it that has cones sticking into the ball from outside the ball. So this is a convex body, right? But it has these 2 points. But I could do it again. For example, I can stick another point here, and I can create another cone, and I can do this as many times as I want, as long as these hats that you put on the ball don't overlap with each other. Okay. And so what you've done is you've taken a ball, but you've made it wider by pulling out these corners out of the ball. And these bodies are the bodies that minimize surface area under a mean width and a volume constraint. And they have a name. They're called cap bodies because they have caps on them. Technically speaking, these are cap bodies of the ball because you can take another body and pull points out of them. And these are very strange. If you're used to thinking about isoperimetric theorems, these are very strange bodies because, the solution to this problem is now you see very non-smooth. It has these corners, which are non-smooth. It is highly non-unique, right? Because you can put these caps on the ball in many different ways to get the same volume and surface area. These bodies are not symmetric, right? Usually solutions are symmetric. So everything that you think you know about isoperimetric theorems goes out the window when you ask these type of questions. So these are very strange objects, and yet this theory is very old. So this theorem that I wrote down here, it was proved in part by Minokwski in the very original, one of the, let's say, most earliest papers in the field of convex geometry in 1903. He proved sufficiency that these bodies do minimize surface area under those constraints, and necessity that these are the only bodies that do that was proved by Bull in 1943. And that was a conjecture that was open from Minokwski, and many people worked in that in between. And nowadays, this type of result is not very well known. It's a bit of a curiosity, but at one time, this played these type of questions played an important role in the history of convex geometry and also of isoperimetric inequalities. For example, in the famous book of Polya and Szego about isoperimetric inequalities, this result is mentioned on page 1. So this is a sort of very classical result in this area. But from the point of view of this talk, this is just a motivation or an initial motivation, or let's say an amusing example more of much deeper ideas and questions that lie underneath it, and those are what I want to describe next. Okay. So just a teaser in a sense. So let's start by talking about what are these geometric quantities that one is interested in. Okay, so volume, surface area, mean width. These are just 3 examples of geometric quantities associated with convex bodies. And the general class of quantities that arise here come from a very important observation of Minokwski. So let's take some convex bodies, M convex bodies in Rn. Okay, and one of the most basic observations of Minokwski that comes from this 1903 paper is that if you look at the volume of convex bodies, that volume is a polynomial as a function of the convex body. Okay? And what this means is that if I take the volume of a linear combination of these bodies with positive coefficients, so this plus over here just means that I'm taking the set. This is the Minkowski sum. So I'm taking the set of all points of the form lambda 1 x1 plus lambda 2 x2 until lambda m xm, right? Where x1 is from k1, x2 is from k2, etc. Right? So if you take a linear combination of these bodies and you take the volume, then this can be written as a polynomial, a homogeneous polynomial of degree n, the dimension in these coefficients. So it's the sum of I1 to In is 1 to m of lambda I1 to lambda In times some coefficients. And these coefficients depend on the convex bodies K, Ki1 through Kin. Okay? And these coefficients over here are called mixed volumes. So these are the coefficients of the volume polynomial. And the basic observation of Minkowski, once you understand that volume is a polynomial, then of course studying the volume of convex bodies, it's natural to think about this in terms of studying the coefficients of the polynomial. And these coefficients have all sorts of geometric meanings. Okay, so for example, the 3 parameters I've already discussed are just very special examples of mixed volumes. So for example, the volume of a convex body K is just a mixed volume where I plug in the same body K for all of the n parameters of the mixed volume. But if I take the surface area of K up to some numerical constant, depending only on dimension, I think it's just n, but I always forget what it is. I have to compute it. But this is the mixed volume, where what I do is in one slot I plug a Euclidean ball, so B is a Euclidean ball, and in the remaining slots, n-1 slots, I plug the convex body, then I get the surface area. And the mean width of a convex body, you get that up to an absolute constant, depending only on dimension, if I plug in a Euclidean ball for all of the parameters except one, where I plug in the body. And there are many, many, many other of these type of geometric parameters. For example, if I have some finite number of balls and then, some number of balls, not one or n-1, some number of balls and some number of bodies, I get the averages of volumes of projections onto lower dimensional subspaces. But if I take other combinations not involving just one body and a ball, but other combinations, then you can get all sorts of other types of geometric parameters, right? So you can think of the sort of this as being a very big class of geometric parameters associated with convex bodies, which just arise as the coefficients of the volume polynomial. And they have some important properties which are very basic. So first of all, what's not obvious, the only property I'm about to discuss that's not obvious right now is that they're non-negative. So the coefficients of the volume, not just its volume of polynomial, but the coefficients are non-negative. This requires proof. But they're symmetric. Symmetric means that you see the mixed volume in dimension n is a function of n convex bodies, right? But the order doesn't matter. This just follows from the definition, because you see in this monomial, of course, the order doesn't matter. They're translation invariant. So if I take one of these convex bodies, Ki, and I translate it, it doesn't change the mixed volume. This is obvious because it's also true for the volume, right? So this is just inherited from the volume. It's translation invariant, and it's multilinear. So if I just take one of these slots in the mixed volume and I stick a linear combination of bodies in that with positive coefficients, then that's just a linear combination of the mixed volumes, which also follows basically from the definition of these mixed volumes, right? So these objects have very basic properties, and they encode all sorts of geometric information. Now, once you understand that these are basic objects in the theory, then of course, if you're Minokwski and you've just discovered this, then you start wondering whether, you can express geometry in terms of inequalities between these coefficients, right? So for example, the classical isoperimetric inequality can be expressed as an inequality between surface area and volume, right? The volume to the power n-1 over n is bounded by a constant times the surface area, right? So this is an inequality between two mixed volumes, right? So you might wonder what other inequalities exist between mixed volumes. Are there some general inequalities between mixed volumes? And the answer is yes, there are many inequalities between mixed volumes, but sort of the uber inequality in this business is the so-called Alexandrov-Fenchel inequality. It appears to be horribly misnamed because the Alexandrov-Fenchel inequality was actually first discovered by Minokwski in dimension 3, okay, much earlier in 1903. And Fenchel never published a proof of this inequality. He published an announcement of a proof that I tried to read and I couldn't make any sense of whatsoever. And he never published a proof, and Alexandrov published a proof. So it should be called the Alexandrov inequality. The problem is Alexandrov has so many inequalities named after him that it would be hard to understand which one. So we tack on Fenchel and we just, Minokwski also has many inequalities. So we omit him. I don't know. This is historical. I can complain about it, but I'm still going to give it the standard name. So the Alexandrov-Fenchel inequality, it's a general inequality between mixed volumes. What does it say? It says that if I take the mixed volume...
Can we say how it was called? It was called...
How is what called?
It was called once quadratic Alexandrov inequality. But we started to mention name of Fenchel too. Perhaps he asked a question.
Vitaly is a little bit, Vitaly gives us the Russian perspective, which is perfectly fine. But in the German literature, Vitaly...
No. It is German. This name going from one German mathematician, not from Russia. Russian accepted this double name, and I also don't know. For example, I don't know who invented question. Hilbert did not know question, because he would prove this immediately. He knew. Prove it.
Okay. But this is a discussion.
Fenchel involved question. So this is perhaps his part. But his proof has no sense. It is known now.
Let us postpone this discussion for the lively after talk. Okay. It is a little bit, for example, if you look in Bohl's paper, he calls this the Fenchel inequality, and Alexandrov is not mentioned. So There are many names that have been used in literature, but for better or worse, this is the name that is being used nowadays, the Alexandrov-Fenchel inequality, and the history is very interesting, and then we can discuss it later. Okay, but here it is. It's a quadratic inequality, right? So on the left-hand side, you have, so you have to notice that this is an inequality for convex bodies in Rn. So there are n bodies in each of these mixed volume, but they play a different role. The first two bodies vary, right? So you have KL on the left-hand side and KK and LL on the right-hand side. But these C1 to Cn minus 2, these are reference bodies, and they play a separate role. They're fixed. They're the same in all three terms. Okay. But of course, you can take this inequality where you only vary two bodies, and you can combine them in different combinations, and then you get inequalities where you vary more bodies. Okay, so there are many more general inequalities that can be derived from this quadratic inequality. This is sort of the basic inequality in the theory. And it looks sort of like a reversed Cauchy-Schwarz inequality, right? If this were a quadratic form of K and L, and the inequality sign would be reversed, this would be Cauchy-Schwarz inequality, but it goes the other direction. So this is the Alexandrov-Fenchel inequality. And already in the very beginning, so it was proved by Minokwski in dimension 3, by Alexandrov in any dimension. And already at the very beginning of this theory, there was the basic question, for which bodies KL C1 to Cn minus 2 do you get equality? And this question, you find it either implicitly or explicitly. So in Minkowski's original paper, this question was not asked explicitly, but it was asked implicitly in the sense that he studies special cases of all the special cases he knows how to prove, he studies explicitly. So the question is clear. In Alexandrov's paper, this question is asked explicitly. We don't understand. Alexandrov writes something like, we don't know the severe difficulties arise in understanding the equality cases of this inequality. In fact, it's not even known in the setting of Minkowski, is what Alexandrov writes in his paper. So these questions have been there from the very beginning. And what is the significance of such questions? Well, let me just give you the simplest example that we've already discussed. So let's do it in dimension 3. So the dimension, this is the setting of Minkowski's paper. So what is one inequality we can write down like this? Let's take the mixed volume of a Euclidean ball and two copies of a convex body K. Right, so I fix the last body K and I vary the first two. So this is greater or equal VBBK times VKKK, right? And now I remind you that this object over here is proportional to the surface area of K. This object over here is proportional to the mean width of K. And this object over here is the volume of K, right? So here is an inequality between these three geometric parameters that I wrote on the first slides, right? Surface area, volume, and mean width. And now you can ask the question, say that I fix the volume and the mean width. Those are the two parameters on the right-hand side. Say I fix them to be two different numbers, right? And the right-hand side is fixed. Then the surface area of any convex body squared is always greater or equal than the product of those two numbers, right? And so when is surface area minimized under those constraints? Well, it's exactly when this inequality becomes equality, right? And so this extremal problem I wrote on the first slide is just equivalent to studying the equality cases of this inequality, because this is a sharp inequality. And the theorem of Minkowski and Bohl is that equality, in this particular special case, equality, in this particular special case, holds if and only if K is a cap body of the ball. So this explains the theorem on the first slide in dimension 3. Okay, and so you see that these equality cases, they encode extremal problems for convex bodies. And so you know, the inequality we know, it always holds, but we cannot solve the isoperimetric problem, right? The actual minimization problem, unless we understand the equality cases of this inequality. And that is where the question basically comes from. And now if you wanted to do this in higher dimension, this special case of surface area, mean width, and volume holds in any dimension, but then you have to combine different Alexandrov-Fenchel inequalities. So you have to understand more equality cases. The classical isoperimetric inequality also follows by combining several different cases of Alexandrov-Fenchel, etc. So you know, you can build up much more complicated inequalities by combining different cases. But this is the basic question. Now, one thing that I wanted to discuss in more detail, but when I was preparing the talk, I realized there is no way I'm going to have time to do this, is that the Alexandrov-Fenchel inequality actually has very unexpected applications in other areas of mathematics. It turns out that particularly when the convex bodies that you plug in are polytopes, which is sort of the more discrete setting, mixed volumes can encode, they're very good at counting things, which is a very non-obvious fact. So for example, there's a very fundamental theorem in algebraic geometry that says that if I have a system of polynomial equations, n polynomial equations on Cn, and I want to count the number of roots of these equations with some generic coefficients, then this number of roots is expressed by a mixed volume. And then this inequality will tell you something about numbers of roots of systems of polynomial equations. And similarly in combinatorics, there are various combinatorial problems that where you can count certain objects and you can express them as mixed volumes of polytopes. So some examples are certain questions about partially ordered sets, certain questions about matroids. There are various other questions of this kind that relate to the Alexandrov-Fenchel inequality and where the Alexandrov-Fenchel inequality provides very non-trivial information. In fact, an interesting theme that has been very popular recently in algebraic geometry and in combinatorics is that there are analogues of the Alexandrov-Fenchel inequality outside convexity, right? So on the one hand, some questions outside convexity can be phrased in terms of convexity, but conversely, some questions which cannot be phrased in terms of convexity, you can extend the convexity theory. You can find analogues of it outside convexity. And it's a very interesting question, whether the type of things I'm going to discuss hold there. Right? But to get back to the point I'm trying to make here, so if you have, for example, a combinatorial application of the Alexandrov-Fenchel inequality, right, then this translates into an inequality between certain, quantities of enumerative combinatorics, right? And then if you understood the equality cases, then what you would get is then a statement about extremal combinatorics, about for which type of combinatorial structures are these quantities minimized, right? So understanding these type of extremal problems is not just of interest in convexity, but it's also of interest in applications outside convexity. We have a sort of a very funny example of that in the paper, but I'm not going to have time to discuss it, unfortunately. But I just wanted to make this point. So the question is about extremal problems. All right. So let me just say a few words. I'm not going to give you an extensive, history. So I told you this question. The question is originally due to Alexandrov, who states it in his paper, 1937, and in fact, implicitly, it appears in 3 dimension in Minokwski's paper in 1903. You can find a lot of people like Bohl worked on this special case. So it turns out this special case, the solution doesn't help you at all in solving the general problem. It's completely special. If, for example, in the book of Loritz and Fenchel, this was the first textbook on convex geometry. There's a lot of attention played to what special cases of this they were able to prove at the time. But there was no general conjecture. I think nothing whatsoever would have happened in this field if Schneider had not formulated a general conjecture. So in a very beautiful paper in 1985, Schneider states a conjecture about what the equality cases should be. We know they must be very strange because we already get these cap bodies and who knows what else can happen, right? So Schneider stated a general conjecture, but it's only been proved so far in very special cases. Okay? There was a little bit of progress initially, but the main sort of part of the problem has remained pretty much open since then. Very recently with Yair Shenfeld, we started working on this. We made a considerable amount of progress, and I want to talk about one aspect. So we have a few different directions in which we made progress. And I want to talk about sort of the most complete direction, which I'm going to explain next. So, but we started working on this a few years ago at MSRI, and I got sort of obsessed with this problem. And one of the things I really liked about this problem is that it seems to have it seems to have its feet in many different areas of mathematics. It's not just a question about pure convexity. It's connected to geometry. It's connected to analysis because there's an analysis involved. It's connected to combinatorics. It's connected to algebra. So it has a very interesting combination of different problems, and those problems are in some sense seem to be separate from each other. And what I want to talk about today mostly is about the combinatorial aspect of the problem. And so what we managed to do. One of the things we managed to do is to completely settle all of the equality cases of the Alexandrov-Fenchel inequality in the case where all of the convex bodies are polytopes. Actually, we only need the reference body C1 to Cn minus 2 to be polytopes, but let's not worry about that for now. Let's assume that all of the bodies are polytopes. And this is exactly the case that's needed in all these combinatorial applications, for example. So, and in fact, the conjecture is that the equality cases for general convex bodies are more or less the same as in the case of polytopes once you write down the correct definitions. And if I have time at the end, I'll try to explain that. But what I want to focus today on the case where all the bodies are polytopes. So, so today, let's assume all bodies are polytopes, and let's see what we can say. So normally when I would give such a talk, I would at this point write down a theorem and explain to you what the theorem is, and then I would talk about how you might prove it. But it's a little bit difficult because there's so many of these equality cases, right? That it takes a long time to write them down. So I'm going to go backwards. Okay, I'm going to talk a little bit about what the equality cases could be, and then I will postpone writing down some sort of theorem until the very end of the talk. Okay, so once we've discovered a little bit what the issues are that arise. So what are the equality cases? So so the equality cases or the extremals. So the question we should ask ourselves, what are they? Right? And so what are we trying to understand? We're trying to understand what happens when you have that the mixed volume of K L C1 to C is equal, right? It's always greater or equal. That's the Alexandrov-Fenchel inequality. But what happens when they're equal? Right? So when are they equal? So there's a few easy cases. Okay, so let me call them the trivial extremals. So they're trivial, but they're still important. Okay, so what are the trivial cases? So the first trivial case is when both sides are zero. This is a special case that has to be handled separately. This is sort of the trivial case of the inequality when both sides are zero. And this case is relatively easy because we do understand very well, it's a sort of an elementary fact about mixed volumes when the mixed volume of convex bodies is zero. Right? Now, let me emphasize at the outset that unlike volume, so the volume of a convex body is zero if and only if the convex body lives in the lower dimensional subspace, right? But that's not true for mixed volumes. It's perfectly possible to have mixed volumes of convex bodies that live in lower dimensional subspaces and the mixed volume is positive. And this is just because you can take the Minkowski sum of different bodies in different lower dimensional subspaces and they can add up to a full dimensional body, right? So it is not necessary that the bodies are full dimensional for the mixed volume to be positive, but the characterization of when the mixed volume is zero is a purely dimensional one. It has to do with the dimensions of the bodies. So if I have the mixed volume of n convex bodies, it's zero. This happens if and only if. So each of these convex bodies might lie in a different affine space, right? They might lie in the lower dimensional space. So let's call these spaces the affine hull of K1, the affine hull of K2, the affine hull of Kn, right? So these are the subspaces in which these bodies live. So the mixed volume is zero if and only if these, or let me characterize maybe when it's positive. No, let me characterize when it's zero. Let me characterize when it's positive. So the mixed volume is positive if and only if the affine subspaces in which these bodies live contain linearly independent directions. Right, so that means that in each one of these lower dimensional subspaces, perhaps, I mean, they could be full dimensional, you can find a direction so that the different directions are linearly independent. And this is a basic characterization that is, something that you prove when you first learn about mixed volumes. And so we understand very well when mixed volumes are not positive, and so we can characterize when both sides are zero. Okay, and I spelled it out because we will need this characterization of when mixed volumes are zero later. So that's why I gave this. But if you don't want to remember the details, just remember this just has something to do. When our mixed volume zero, it's somehow when the different bodies degenerate into lower dimensional subspaces that are not linearly independent, right? That's when mixed volumes are zero. Now, there's another very obvious equality case, which is when K is equal to L, right? Obviously, when K is equal to L, you have equality, right? Because then you have VKK squared equals VKK times VKK, right? That's obvious. But remember that mixed volumes are translation invariant, right? So it's enough if not k is equal to L, but k is a translate of L. Right? Moreover, mixed volumes are linear, right? And this equation is homogeneous. If I multiply k by a constant, by a positive constant, the left-hand side multiplies by that constant squared, and the right-hand side also multiplies by that constant square, right? So the equation is also invariant under scaling. So there's a trivial equality case, which is when k is some constant times, when k is some positive constant times L, plus v, so v is a vector, right? So when k is homothetic to L, right? When k is homothetic to L, just because this equation is invariant under translation and scaling, right? So we have to take these invariances into account, right? So if k is equal to L up to translation and scaling, then we obviously have equality. You can see it directly in this equation. Okay. So these are the trivial equality cases. And maybe you would think, well, maybe these are the only equality cases. But in fact, there are many, many more, as we know, because we have cap bodies and other things. So where do these come from? How should you think about this? Well, for example, here you see that you get trivial equality cases because the equation has some invariances, right? The equation is invariant under translation and scaling, right? So those symmetries must be present in the equality cases, right? Now, what I'm going to do next is I'm going to discuss another type of invariance of mixed volumes that is not obvious. Okay, and so this is a non-trivial invariance. So just like mixed volumes are invariant under translation and scaling, I'm going to now show you another transformation that mixed volumes are invariant under, which is not obvious and which causes you to get a lot of non-trivial equality cases. Okay. So what is this invariance? Well, remember that mixed volumes are linear functions of the convex bodies. Right? So the mixed volume, if I view it just as a function of one of the bodies, is linear. Right? So how do we think about this, right? So you would want to express the mixed, so you might want to know how the mixed volume depends as a function of one body. This must be a sort of linear function. So the best way to think about this is in terms of support function. So let me remind you or define it for you. So this is a basic idea. The support function of a convex body is the function hk of x. So for every body k, you have a convex function, which is just a supremum of y and k of the inner product of y and x. Right? And we view this as a function on the unit sphere. Okay. And what is it? Well, it's easy to understand geometrically. So if this is the convex body, and let me draw in this case the origin. So that dot over there is the origin. It doesn't have to be inside the convex body. It could be outside. So let's pick a direction x. So this is a direction x in the unit sphere. So what I can do is I can look at the supporting hyperplane of this convex body that has normal direction x, right? So this is the supporting hyperplane of that convex body that has normal direction x, and I can look at its distance to the origin. So this distance of the supporting hyperplane to the origin, that's exactly hk of x. And what this means is that if I know the function hk for all x, right, then I know the distance to the origin, the sign distance to the origin of the supporting hyperplane in every normal direction, which means I know the convex body, right? Because the convex body is the intersection of its supporting half spaces. So the support function uniquely determines the convex body. Right? Support function uniquely determines the convex body. And moreover, it's clear from the definition that the support functions are linear. And similarly, if I multiply by a positive constant, they're homogeneous, right? So the support functions behave linearly under the addition of convex bodies, right? So I could equivalently view, right, rather than viewing the mixed volume as a function of the convex body k, I could view the mixed volume as a function of the support function hk of the convex body k. And because this is a linear function, right, there must be a kind of representation theorem that says that I can write this as a linear functional of the support function, or in other words, an integral of the support function. Right? And now I remind you that we've restricted attention to polytopes. So I'm just going to write down the formula for polytopes. This is a general formula, but let me write down the formula for polytopes. So for polytopes, there's a very nice explicit formula which says that the mixed volume of k, L, C1 to Cn minus 2, what is it? it's 1 over the dimension times the sum over all directions in the unit sphere, I'll clarify that in a moment, of the support function at x times the mixed volume of the faces of the bodies. So this FLX means the face of the polytope L with normal direction x. And so here you see you have the faces, if these are n dimensional bodies, the faces can be at most n-1 dimensional, right? And this is a mixed volume of n-1 convex bodies that are n-1 dimensional. So that is correct, right? And I wrote a sum over all vectors in the unit sphere, but of course in most directions, some of the faces are going to be zero, vertices, and this mixed volume is going to be 0. So in fact, there's only a finite number of directions in which these mixed volumes of the faces are positive. And so this sum makes sense. And this is the Riesz representation. Let's call it the Riesz representation of the linear function of the mixed volume as a function of one of the convex bodies. And when you have this representation, there's a very important observation that you should make, is that the mixed volume depends not on the whole function hk. It doesn't depend on the whole function hk. It only depends on hk of x for a finite number of x. Right? In the case of polytopes, it's exactly for those x's for which these mixed volumes of the faces are positive. So what this means is that the mixed volume doesn't depend on the whole convex body K. It only depends on its supporting hyperplanes in a few directions, and those directions are determined by these convex bodies over here. So that means that what I can do is if I take two convex bodies K and let's say another K, right, two convex bodies K that have the same supporting hyperplanes in these directions, but may be completely different in other directions, they will have the same mixed volume. And this is a very, this is a non-trivial invariance of mixed volume. So let's give it a formal definition. Okay. So what is the definition? Let's call a vector x in the unit sphere L C1 to Cn minus 2 extreme. This definition makes sense for polytopes. If what? Well, I want to call it extreme if this mixed volume V of the faces of L in the direction x to Cn minus 2 in the direction x is positive. Right? So I call a vector L C1 to Cn minus 2 extreme if that vector shows up in this sum in the definition. Right? But remember, I gave you the characterization of when mixed volumes are positive. I gave it to you for n-dimensional convex bodies, but we can of course apply that definition to the n-1 dimensional faces or the lower dimensional faces, right? So we call it extreme if the face of L in direction x, the affine Hall, right? So the linear subspace or the affine subspace in which that face lives, and all of the other affine subspaces of the faces contain linearly independent directions. So this is a geometric characterization of which vectors x show up in the representation of mixed volumes, right? And it has to do with not with the dimensions of the convex bodies, but with the dimensions of the faces in the directions x. And then it's obvious from the formula, right? So what should I write? That if I have two convex bodies, K and K tilde, have the same supporting hyperplanes in all L C1 to Cn minus 2 extreme directions, right? This is equivalent to saying that the distance to the origin of the hyperplanes in these directions are the same for the two bodies, right? So that means that hk of x is equal to hk tilde of x for all x that are L C1 to Cn minus 2 extreme, right? And you see that if the two support functions are the same in these directions, then the mixed volumes must be the same, right? And they must be the same because it's only the sum over the support function in these directions that shows up in the formula on the previous slide. And this is a non-trivial, it's a non-trivial invariance of the mixed volumes, right? Because it shows that the mixed volume as a function of the first body, right? The remaining bodies fix a finite number of directions in the case of polytopes. And the mixed volume only depends on the supporting hyperplanes of the body in those directions and not in other directions. So you can have two bodies K and K tilde that agree in those directions, but are completely different in the other directions, and they will have the same mixed volume. And because you have a non-trivial invariance of mixed volumes, this will translate into a non-trivial invariance of the Alexandrov-Fenchel inequality. And that non-trivial invariance gives rise to a large number of non-trivial equality cases, right, of the Alexandrov-Fenchel inequality. And I come back to the conjecture of Schneider. Schneider's conjecture was that these are the only equality cases. Right? So let me write down what Schneider's conjecture is. And I'll give an example in a moment where you'll see what this means. So Schneider's conjecture is what? That you have equality VKK times VLL if and only if, right? So remember, you have equality here if K is equal to AL plus V, right? If K is homothetic to L. But now you see we can make that weaker. We can say that K doesn't have to be equal to AL plus V. It only has to have the same supporting hyperplanes as AL plus V in enough directions. Right? So if K and some homothet of L have the same supporting hyperplanes in all directions, that are what directions? Well, they have to be extreme, but with respect to what bodies, right? Because I have to replace the K here, but I also have to replace the K here. And these two mixed volumes has two different sets of extreme directions, right? So let's combine them. So the statement of the conjecture in all directions that are M C1 to Cn minus 2 extreme, for all convex bodies M, or for all polytopes M, okay, right? Because I have two different sets. This M has to be different on the left-hand side and the right-hand side of the inequality. And this is the conjecture. And one direction should now be obvious. This direction is now clear, right? Because if these two bodies have the same extreme directions, then I can just replace K by AL plus V in all of the mixed volumes that appear in this inequality. And we know that we have equality when K and AL plus V are homothetic. And the other question, the other direction, is the big question. Why should these be the only equality cases? And let me give an example finally where you see what this is. Right? Let me give two examples. First, let's look at dimension 2. Dimension 2 is completely understood a long time ago, but let's just look for sanity check. What happens in dimension 2? So in dimension 2, there are no reference bodies, right? The mixed volume is just a function of K and L. There are no C1 to Cn minus 2, right? So then the conjecture is that K and L plus V have the same supporting hyperplanes in all M extreme directions for all M, right? But every direction is M extreme for some M because, okay, maybe I skipped this. If you look at this definition, what does it mean to be L C1 to Cn minus 2 extreme? It means that the faces of L in the direction X, C1 in the direction X, etc., live in subspaces that have linearly independent directions. So if all of the bodies are the same, if L equals C1 equals C2 equals C3, etc., right? Then all of these subspaces, affine hull of the face is the same. And so the definition says that if all of the bodies are the same, right, then a direction is extreme if and only if X is the normal of a face of dimension n minus 1, right? Because it means then I have n minus 1 affine subspaces, but they're all the same subspace. And they must contain n minus 1 linearly independent direction, right? So if all of the bodies are the same, then it means that X is a direction of a facet, right? Of an n minus 1 dimensional face of the body, right? So if we're in dimension 2 and I have m extreme for all m, that means that the direction is a facet of some polytope, but every direction is a facet of some polytope, right? So in this case, all directions are m extreme for some m, right? Which means that the conjecture would then state that k and al plus v have the same supporting hyperplanes in all directions, which means they must be the same. Which means that in 2 dimensions, you should only get trivial equality cases. And this is true. This was known very, very long ago. And this is easy to prove. 2 dimensions is a very special case. But it's consistent with the conjecture, right? So in 2 dimensions, nothing interesting happens, right? The only equality cases are the trivial ones, and nothing interesting happens, but it's still a good sanity check. And there's a reason why I'm showing you this stupid example. You'll see it in a moment. But let's look what happens in dimension 3, for example. So in dimension 3, what are the relevant directions? The relevant directions are directions that are MC1 extreme for some m. So if you go back and look at the definition, this means that the dimension of the face of C1 in the direction x is greater or equal than 1. Okay. So, right. So it is. So the direction is a relevant direction for this conjecture if it is normal to a face in. So we're in dimension 3 now, and the relevant direction is one that's normal to a face of the reference body C1 in dimension at least 1. Now, the only directions that are not these directions are directions that are normal to a face of dimension 0, which is a corner. So this means that this is equivalent to say that x is not normal to a corner of C1. So these are the relevant directions. And then what does the conjecture say? That the only equality cases are those where k and al plus v have the same supporting hyperplanes in all directions except those directions that are a corner of C1, that are normal to a corner of C1. So let me just give an example. So let's give C1, let's just make this the usual cube, the nice polytope. Right. And now what I'm going to do is for k and l, I'm going to take the cube, but I'm just going to shave off some of its corners. Right. So for example, I can take this one, where I've shaved off this corner, right? So I've just taken the original cube, but I've just sliced off one of the corners, right? And maybe for L, I can do the same, but I can slice off another corner. Like that. And so here for K and L, I've sliced off 2 different corners. So now let's look. So what are the supporting hyperplanes? What are the directions that are not normal to a corner of C1? So these are just directions which are normal to one of the edges of the cube. But you see, if I look at the supporting hyperplanes of the 2 body K and L in directions that are normal to an edge of the cube, well, all of these bodies have edges in the same places as the edges of the cube. So those supporting hyperplanes are the same for K and L. Now, what is different is if I took a supporting hyperplane in the direction that was normal to one of these new faces that have been introduced, right, by slicing. If I took, for example, supporting hyperplane that's normal to this face, right, then, and here I have a corner. These are in 2 different places. But the directions that are normal to these new faces that are created, they're always normal to a corner of the original cube, C1. And so those directions don't count. So I can do this with impunity, right? I sliced off 2 corners arbitrarily. I can slice off these corners any way I want. As long as I keep a little bit of edge in every direction, these are all going to be equality cases of the Alexandrov-Fenchel inequality. Okay. And we know they are going to be because this direction, the left direction, is clear. We have already proved this. Right? What's not clear is that these are the only equality cases. Right? But here you see what is going on. And let me just remind you, even though they're not polytopes, that when you go to the, when you think about the cap bodies, you have exactly the same story. So let me hide that here underneath, right? If you recall the cap bodies, in the case of the cap bodies, C1 was, for example, a body with one of these corners sticking out, right? And K was the same thing. right? And L was just a ball. That was the example of the cap bodies. And you see that K and L, if I look at the direction that is not normal to the corner, K and L have exactly the same supporting hyperplanes, right? But if I look at the direction that's normal to a corner, K and L have very different supporting hyperplanes, right? But those directions are normal to a corner of C1, so they don't count. And so this story explains, even though cap bodies are not polytopes, but we have a similar story for general convex bodies. This story explains exactly why cap bodies show up as the equality cases, right? It's because the corner, as soon as the body has a corner in dimension 3, right, it's the normal directions to that corner no longer play a role in they give you an invariance of the mixed volumes, and so the bodies can differ in those directions, and it doesn't change the equality cases. But in all directions where the body C1 doesn't have a corner, the two bodies have to have the same supporting hyperplane, and then you indeed see that in this example. Right? So this explains that. Good. So I hope this gives you some sort of flavor. So far I've only told you what is the conjecture. And now in the last 10 minutes, I have to explain to you everything else. So what is true? How do we prove it? So that's not a lot of time. So here's what I want to do. What I want to do, rather than write down a theorem for you immediately, I want to write down for you a sort of, let's say, a caricature of how we do the proof. And then I'm going to try to convince you that this caricature makes no sense whatsoever. Okay. So remember, I have not actually stated a theorem for you, right? I've just stated a conjecture. But let's pretend for a moment this conjecture is true as written, and let's think about how we might prove it. So here's a caricature of how we prove such a statement. So there's two steps. So the first step, so the caricature of the proof in big terms is that we just prove it by induction on dimension n, right? So we have an equality case in n dimensions, right? And how are we going to prove it? Well, suppose we've characterized all equalities in dimension n minus 1. Then we somehow want to relate the equality cases in dimension n to the equality cases in dimension n minus 1. And reason by induction on dimension. And this is in fact what we do. And here is a caricature of how we do it. So what is the relation? This is now the question. What's the relation between the equality case in dimension n and the equality case in dimension n minus 1, right? So what we might show, for example, at least that would be great, what we might show is that if you have equality for the bodies K, L, C1 to Cn minus 2 in the Alexandrov-Fenchel inequality in dimension n, then for all vectors V, if I were to project these bodies onto the orthogonal complement of V, that's an n minus 1 dimensional space, I would get equality of that n minus 1 dimensional Alexandrov-Fenchel inequality. So if I take the projection onto V, the orthogonal complement of the direction V, K, projection on V perp L, projection on V perp C1, etc. Right, so these bodies over here, they live in an n minus 1 dimensional space, right? I've taken the orthogonal complement of a single direction in Rn, right? So these live in n minus 1 dimensional space. And note that I didn't go up to n minus 2, I went up to n minus 3. So these are n minus 1 bodies. So these are equality in dimension n minus 1, right? So there's an Alexandrov-Fenchel inequality for these projections, right? These are n minus 1 bodies in Rn minus 1, or in an n minus 1 dimensional subspace of Rn. So we can write down an Alexandrov-Fenchel inequality for these. And the claim sort of is that if I have equality in dimension n, then all projections onto hyperplanes form equality in dimension n minus 1. And if this were true, right, then we could just go from dimension n, right? We could say, okay, we start in dimension n, then we conclude that in dimension n minus 1, we have, by induction, we know what the equality cases are in dimension n minus 1, so we characterize these projections. But we can do this for all directions V, right? So we can characterize the projections of their equality cases in all directions V, right? And then the second step, we somehow glue together the information in these projections to construct the full dimensional bodies, right? But you can imagine if I've characterized the projection of K and L in all directions, then in all onto all hyperplanes, then I've characterized K and L, right? So So first you have to engineer the induction hypothesis, and then you have to glue things together. Now you should be a little bit suspicious because you see I started with n bodies, but in n minus 1 dimensions I should have n minus 1 bodies. So I just removed one, right? So what's really true, it's still not true. I'm about to explain that, but the role that's played by the body that I've left out is that it constrains the directions in which you can do it. You can only look at those directions that lie in the subspace of the body that you left out. But let's pretend for a moment that all the bodies are full dimensional, okay? And then this doesn't play anymore. Okay. So this looks great, right? You know, we do induction on dimension. Everybody's seen proofs by induction on the dimension. You know, this is you know, so it looks plausible, right? And now I'd have to show you, you know, how we prove such things, right? You know, I wrote down an induction hypothesis. Okay, if we can prove it, then we're done, right? Now, what I want to argue to you is that this makes no sense whatsoever. If you've come to me 2 years ago and told me that you're going to prove this like this, I would have told you that's completely impossible. And why is it impossible? It's because they're actually both steps have huge problems, but step 1 is conceptually the biggest problem. And the problem with step 1 is that it's simply not true. It's simply not true that if I start with equality cases in dimension n, and I look at the projection onto n minus 1 dimensional subspaces, I get equality cases in dimension n minus 1. And to see that, we just have to go back to the previous page and look at this example over here at the bottom with these cubes. You see, I mean, let's take, for example, let's take a direction that is, for example, tangent. It lies in the subspace of one of these, right? It's tangent to one of these new faces, right? So if I project, for example, this body L onto a direction that's tangent to that new face, the projection will be a 2-dimensional polytope that has a face, a facet in that direction. But this guy over here will have a corner, right? So I get 2 different bodies that are not the same by translation, up to translation and scaling. But in dimension 2, all of the equality cases are trivial. They must be the same up to translation and scaling. Right? So it's obvious just by looking at this picture that it's just false, right? I mean, there certainly exist directions in which it's not true that if I project the equality case in those directions, I get the equality case in dimension 2. Right? And in fact, it's not just that there exists such directions. It will happen in a lot of directions, right? Because there's nothing special really about taking the direction parallel to one of these faces. I can rotate it a bit. Nothing will change about this story. Right? So actually, in most directions, this is false. Right? And as soon as this is false, you know, you can just see it. I mean, it seems like the whole story is going to collapse completely, right? I mean, we have here a program, but the program looks nice, right? But the problem is it's simply not true, right? That if you project the equality cases in dimension n, you get equality cases in dimension n minus 1. I mean, you just check it on the first example you can think of. And I would say, you know, I mean, how would you attack such a problem? You know, probably the first thing you would go to the classical proofs of the Alexandrov-Fenchel inequality and try to see what happens. It's very hard to see what happens there because the classical proofs of the Alexandrov-Fenchel inequality work by approximation. And when you make the approximation by nice bodies, all of the interesting equality cases disappear. For example, it works for smooth bodies. It works for polytopes that have the same face directions. Under very strong constraints, and these assumptions that are made in the classical proofs cause all of the interesting equality cases to disappear. And as soon as you go to cases where you get interesting equality cases, you know, everything becomes singular. It just becomes a mess. It's not so clear what's going on. But at the heart, I think that this is the explanation for why this problem is strange. The explanation, in some sense, or an explanation, is that there's no obvious relation between the equality case in dimension n and n minus 1. Right? When you project, for example, by projection, by faces, I mean, you can look for it, but it's not clear how you're going to pass from dimension n to dimension n minus 1 when it's not clear what is the relation between these 2 cases. So very quickly, let me outline how we get around this issue. How we get around this issue is the following. Right? So it's not true but what we can prove is that if KLC1 to Cn minus 2 is equality in dimension n, then we can modify K. Then there exists a K tilde that has the same supporting hyperplanes as k in all of the relevant extreme directions, right, such that k tilde L C1 to Cn minus 2 satisfies step 1. Okay, so that the projections of this new body k tilde do become equality cases in one lower dimension. And I should emphasize that if we knew, for example, that Schneider's conjecture were true, then this would be obvious, right? Because Schneider's conjecture says that k tilde must be up to these directions, must be homothetic to L, right? So if we're allowed to modify, we can just take k tilde to be equal to L, let's say, and then it's obvious that you get equality, right? But the point is that we have to prove such a theorem without, right? There's a chicken egg problem. We have to prove such a theorem without knowing what the equality cases actually are, right? Because we don't know that. And it's sort of remarkable that we're able to construct, it's a kind of existence theorem. We're able to construct without understanding the equality cases. We're able to take this k and shift it in the directions that don't matter in order to engineer that this induction step is going to happen. And morally, that is the core part of the argument. And this is, I would say probably the most important idea in the paper, though there are various other ideas that show up. And I'm over time. Let me say in 30 seconds what is actually true. So Schneider's conjecture is not true as stated, okay, but it is true, for example, for full dimensional bodies. And but what can happen is that when the bodies are lower dimensional, you can get new equality cases. And this was actually known just a couple of years after Schneider's paper. Ewald showed a counterexample, and later he found another counterexample. But there was never a conjecture, to my knowledge, about what these lower dimensional equality cases should be. And what happens with these lower dimensional equality cases is that things go wrong in this step 2. That you have you have information from the projections, but they don't glue together nicely. And resolving that, so we have a complete characterization. It's too long for me to write down right now in the time I have, but resolving that issue is what gives rise to new equality cases, that you can glue together lower dimensional equality cases to get new equality cases in higher dimension that are not what Schneider's conjecture predicts. And we have a complete characterization of when this happens and what they look like. But it would take me too long right now to explain that. So I suggest you look at the paper, some pictures that will clarify this. So let me stop there, and thank you very much for the attention, and I'm very happy to take questions. Thanks.